one period, one subsequent period r tau, equal over rt, and suppose you have two groups x and y in R naught, x is above y. They don't have to be adjacent. In RT, R tau, sorry, y is above x, and the two are adjacent. Now you compare this to another history, and all you do is you change R tau to R tau prime. Everything else is unchanged, and the only change you make here is you have an elementary change that just swaps the positions of x and y. So you get x is above y. Everything else is unchanged. This now is, in a very clear, intuitive sense, closer to R naught than this is, because you've moved x closer to, you moved the relation, the comparison of x and y closer to that comparison. So monotonicity says that sustained mobility here should exceed sustained mobility. That's, we think, is a quite innocuous property. Another property we have, and that's the only one that is definitely more controversial, and it's the one that's the most likely that you might want to modify if you want to come up with alternative measures, and that is related to this property of the cavity distance itself. It requires precisely that, but it requires the extension of that to a multi-period setting. We call it complementarity. And complementarity basically says if you start out with one history and you compare this to another history where you invert all the relations in the subsequent periods, right? So you look at sustained mobility, for a given history, and you add to that, just like we do here, the sustained mobility value that you get if you replace all these subsequent histories, these subsequent rankings with their inverses. What you get is maximal sustained mobility value, which is, of course, according to the cavity distance, which is, of course, t times n minus 1 n over 2. Now you may smell a rat now, because we already used some characteristics of the cavity distance to formulate this axiom. This doesn't give us any sleepless nights, though, because that's what's happening with the original characterization of cavity as well. The probably the most parallel, if you will, axiom that's used in the cavity characterization is what it's often referred to as betweenness. That says if you look at two relations, and the relation that is on the shortest path from one to the other, if you calculate the distance between one point and the relation in between, plus the distance of the one in between to the other end, you get precisely the sum of the two. And again, that's also because this notion of being on the shortest path is expressed in terms of the number of elementary changes you need to do that. So, and the cavity distance is defined in terms of these elementary changes. So this, if you will, redundancy is there not only for us, but for the original cavity characterization. And it's like, well, I mean, I like to say there's no such thing as a free lunch in axiomatics. If you have these properties, I mean, they have to come from somewhere, like it or not. So and this is, we think, analogous. But yes, we are very well aware that this is clearly a property that's more difficult to defend than this one. The final, third property is the normalization condition, and that's essentially the same thing as the normalization condition that is used in the characterization of the original cavity distance, and that just says, well, if you look at, if you compare different objects, the difference should be at least 1. We do exactly the same. So we call it again normalization. And normalization says basically, if you look at initial period R0 and 2 t-tuples of subsequent periods R1 RT, R1 prime, T prime, such that R1 RT is not a permutation of this, or they're not permutations of each other. Then it should be the case that the difference in sustained mobility between those two histories should be greater than or equal to 1. So we cannot, so basically that means we cannot go arbitrarily close to 0 with the values of our sustained mobility measure. And again, this normalization property is almost verbatim one of the properties that can be used to characterize the original Kennedy distance. With one subtle twist, and that's you have to make sure that this is not a permutation of this, because if they're permutations of each other, they have to be treated identical. So you can't have a positive difference. And of course, if there is only one subsequent period that's trivially satisfied, it cannot but be a permutation of itself. And that's all we need, right? So our main result is that these 3 properties characterize the Cavendish distance, or the Cavendish measure of sustained mobility. So a measure satisfies monotonicity, complementarity, and normalization, if and only if the measure is given by our good old Cavendish distance or Cavendish measure of sustained mobility, MK. I guess I have a little time left, right? We said 40 minutes, 20 minutes, but so far nobody has stuck to 40 minutes, so why should I? But I'm not going to go all the way to 60, I promise. But just a little discussion of this result. I already mentioned, clearly, if you think we should look at alternatives, absolutely. The culprit here is complementarity. If you want to change something, that's where to go. Because to me, it seems you can't really change monotonicity, right? Because that's almost a that's a fundamental definition of the whole exercise, right? One criticism that has been raised by a referee at some point was that, well, this measure might make interesting trade-offs. And I'll give you an example, and our response to it. Consider a situation where we have four groups in society and 6 subsequent periods after an initial event. And suppose our initial ranking is X, Y, Z, W. In one history, what happens is, as a consequence of the revolution, everything gets turned around, gets turned upside down. So now W is on top, Z is second, Y is third, and X is at the bottom. And for the rest of time, the effect of this fizzles out immediately, and we're back to the good old or if you will, bad old order. So we revert after one period. Alternatively, consider a situation where we start out with the same initial ordering, but now in each subsequent period we just interchange the top and the second group, second highest group. So we get y, x, z, w until the end of the planning horizon. Now, in both cases, what you get for our measure of sustained mobility, so I should give them different names, so these are the prime values. So, sustained mobility for the first history is, well, we need 6 elementary changes to move from here to here. Right? We need 3 to move x to the bottom. We need 2 to move y to the next to the lowest, and we need 1 more to move z to the second position. And that gets us a total of 6. And nothing happens after that, right? Because these are identical to the original relation, so there's zero mobility between RT and R0 for all t above 1. Now, if you look at the second scenario, you get a change. There's just one change, one elementary change going from R0 to R1, and the same change is present for all subsequent periods. So you get a 6 there as well. Now again, one referee said, well, it's not clear to me that this makes sense, because even though this change is much milder, it is more sustained. But to me, that's not entirely obvious. I mean, no matter what you do, you have to have some trade-off between the magnitude of a change in a period and the extent of time to which it is sustained. Is ours the only possible way? Absolutely not. And we would never dare to claim that. My interpretation of the referee's comment was that sort of implicitly the person may have had in mind that if it's sustained for 6 periods, it may it may be like that for many more periods to come. But if you want to use this argument, you have to look at more than 6 periods. So what I can see, and I think this is probably a very good, to me, a plausible way of